This story is about a question so simple that almost no one thinks to ask it, about a phenomenon that everyone has seen thousands of times, yet almost no one has stopped to truly examine, about how the most ordinary thing can turn out to be the most profound if you allow yourself to pause and look at it differently. There is no discovery here that will overturn the world. There is a slow, quiet gaze at something that has always been before us and from which we have grown used to looking away. Imagine billions of stars, billions of galaxies, space extending in every direction without any visible edge. Each of these luminaries radiates light, each one, without interruption, century after century, epoch after epoch. By any simple logic, their light should add up, overlap, fill the void between them. No matter where we turn our gaze, any point on the sky should eventually run into someone's surface, someone's source, someone's distant glow. In such a picture, there is no place for night, and yet night exists. The largest and brightest phenomenon that could possibly exist in the universe, its own glow, seems to be erased. Between the points of light lies darkness, even and nearly complete. This gap between what should be and what we see conceals an entire layer of physics. It touches the age of the universe, the speed of light, the nature of space itself, and what it means to observe anything at all. One ordinary evening glance out the window conceals questions that science spent 2 centuries seeking answers to, and is still seeking today. Have you ever truly stopped before the night sky, not to find something in it, but simply to ask why it looks the way it does? What do you see there, between the stars? Emptiness, or the trace of something we have not yet learned to read? Listen, this story is about a darkness that turns out to be not an absence, but a message. The night sky is perceived as dark almost reflexively. The gaze habitually slides across the black canvas, dotted with scattered silver points, and the mind accepts this picture as a given, as something so obvious it requires no explanation. People have looked at the night sky for thousands of years, generation after generation, and it seldom occurs to anyone to ask what is perhaps the simplest and simultaneously the most fundamental question one can ask about the night sky. What if the most familiar phenomenon, the dark night sky, is one of the deepest mysteries in physics, one we simply do not think about? Let us approach the question rigorously from the standpoint of scientific logic. A dark sky is not at all obvious. Think about it yourself. Billions of stars exist in the universe, and galaxies literally fill space in every conceivable direction. Wherever you turn your gaze, there should be sources of light everywhere. With such an enormous number of luminous objects, how does the sky remain dark? Why does all that light not add up into a single bright glow? This is not a rhetorical question or a philosophical paradox. Behind it lies an entire layer of physics, cosmology, and understanding of the nature of space and time itself. A layer invisible to the naked eye, yet one that determines everything we observe. It turns out that the idea that the sky should be bright occurred to astronomers long before modern telescopes and astrophysics. Astronomers of the past clearly understood, if the universe is infinite and evenly filled with stars, night should not exist in principle. Imagine such a universe, space extending in every direction without end, with stars distributed everywhere at equal density. In such a model, any line of sight cast in any direction would sooner or later inevitably strike the surface of some star. Whether that happens 1,000 light years away, 1,000,000, or 1,000,000,000, in infinite space, distance is of no fundamental importance. Ultimately, every gaze would meet a star, and if so, the night sky should glow roughly as brightly as the surface of an average star, without a single dark gap, without a single black patch. The picture would not be stars on a dark background, but a continuous, uniform glow covering every point of the sky. This very reasoning came to be known as the paradox of the dark sky, and also as Olbers Paradox, named after one of the astronomers who formulated it with particular clarity and consistency. Olbers was far from the first to think about this contradiction. It has roots in classical astronomy and occupied thoughtful minds for several centuries. But it is through his name that this paradox entered the history of science and remains there to this day. It is important to understand this paradox is not an abstract puzzle detached from reality. It serves as a precise indicator that our intuitive ideas about the universe diverge from its actual structure. The darkness of the night sky turns out to be not simply the absence of light as such, but a consequence of deeper and less obvious properties of space, time, and matter. Where then is the flaw in that simple logic about the infinite, starry sky? The first key to the answer lies in the nature of light itself and the speed at which it travels. Light does not fill space instantaneously. It moves at a finite speed, and that movement takes time, even at what is, by earthly standards, a colossal velocity. In everyday experience, we do not notice this at all. Light from a desk lamp or from the sun reaches us so quickly that there is no perceptible delay, and it seems to us that illumination appears instantly. But when it comes to cosmic distances, the picture changes fundamentally. Every star we see in the night sky right now is a message from the past, written in light that left its source a year, 1,000 years, or 1,000,000 years ago. We are not observing the current state of these objects, but their image from the past. Some of the stars we see tonight have quite possibly long since faded, but their light is still traveling toward us through space, and we continue to see them in the sky. To observe the cosmos is always to look backward in time, and the farther the object, the deeper into the past that gaze reaches. This is not a metaphor. It is a strict physical fact. From this follows something very important. The universe is not infinitely old. It has a finite age and a finite history. This means that light from a vast number of stars has simply not had time to reach Earth yet. It is still in transit. Even if the number of stars in the universe were beyond measure, their combined light could not fill the sky entirely. A significant portion of that radiation is still traveling toward us through space, while another portion comes from objects that existed under conditions fundamentally different from today's. The visible universe is limited not only in space, but in time, and this limitation directly affects the brightness of the night sky. The cosmos is not infinitely old, and this has directly observable consequences. But the finite speed of light is only the first step toward the answer. The stars themselves are also not eternal, and this adds yet another important layer to the overall picture. Even if the universe were infinite, stars within it do not burn forever. Every star follows its own path. It is born in clouds of gas and dust, radiates light for hundreds of millions or billions of years, gradually changes within, and ultimately ends its active existence. This is a universal law. Even the most long-lived and stable luminaries burn for only a limited time. The universe has never been a static collection of permanent light sources. Its luminous contribution has continuously changed throughout cosmic history. In different epochs, the number of active stars and their combined brightness were entirely different. And this continuous change itself rules out the picture of a uniformly glowing sky. The distribution of matter must also be taken into account. Stars are not scattered evenly throughout all of space. They are gathered into galaxies, and galaxies unite into groups, clusters, and superclusters. Between these vast islands of matter stretch colossal, empty expanses where the density of matter is negligible. Light passing through such voids encounters no additional sources and is amplified nowhere. The gaps between stellar systems are so large that light from individual sources almost never overlaps enough to create any perceptible cumulative background. Each star illuminates only a vanishingly small fraction of the surrounding space at any appreciable level. And yet even these explanations are insufficient without accounting for one further circumstance that changes the entire picture fundamentally. Space itself does not stand still. It is changing, and this change directly affects how light travels and how it is perceived. Light from millions and billions of galaxies is reaching Earth right now, but we cannot see it. It has been too greatly altered by the expansion of space to become part of the night sky perceptible to the human eye. One of the most important discoveries of modern cosmology was the understanding that the universe is expanding. Moreover, this expansion is fundamentally different from how we ordinarily picture motion. Galaxies are not flying through space like stones thrown in every direction. Space itself between them is stretching, and it is for this reason that the distances between large structures increase over time. This is a subtle but fundamentally important distinction between motion through space and the expansion of space itself. Light traveling through such an expanding space is affected by this stretching. Its wavelength gradually increases along with the space through which it propagates. This effect has long been known as cosmological redshift. Light from distant objects shifts toward longer, less energetic wavelengths. For the human eye, this means that radiation which was visible at the moment of emission eventually passes into the infrared or even the radio range. This light physically exists, it is real, and continues to propagate, but it is no longer perceived as part of the visible glow of the night sky. The farther the source, the longer its light travels, and the more strongly the expansion effect manifests. For the most distant galaxies, the shift is so great that almost all their radiation falls outside what the unaided human eye can perceive. The expansion of the universe also affects the energy balance of radiation. When the wavelength of light increases, its energy decreases. This is not a loss of energy in the classical sense. It is a direct consequence of the fact that the energy of a photon is determined by its frequency. In stretched space, light becomes less energetic, and its contribution to the overall brightness of the sky decreases accordingly. This process occurs slowly, but it is continuous. All of this together leads to a concept rarely thought about in everyday life: the observational horizon. Beyond the observational horizon lie entire clusters of galaxies. They exist right now, at this very moment, but their light will never become part of our night sky. The observable universe is not identical to the universe as a whole. This is not a philosophical assumption or a metaphor, but a direct consequence of physical laws, above all the finite speed of light propagation. Every observation in astronomy is inextricably linked with a time delay that grows with the distance to the object. Observing a distant galaxy, we see it not as it is now, but as it was at the moment that light was emitted. In a very distant past, there exists a boundary beyond which light simply has not had time to reach us since the birth of the universe. This boundary is called the observational horizon. It is not a physical wall or the edge of space itself. Beyond it, space may well continue, with stars, galaxies, and entire structures existing there. But their radiation is either still in transit or was emitted under conditions that render it inaccessible to modern instruments. The darkness of the night sky is to a significant degree a reflection of this invisible region, a vast space hidden behind a temporal horizon. It is important to understand that even within the observable universe, observations are uneven. The most distant objects detected by modern telescopes belong to early stages of cosmic history. At that period, stars were not yet as widespread as they are today. The first generations of luminaries were only beginning to form, and the space between them remained largely dark. Even the directions that reach the maximum depth of observation are not filled with continuous starlight. They extend into epochs when that very light was far scarcer. In addition to this, it should be noted that the human eye perceives only an extremely narrow band of the electromagnetic spectrum. A significant portion of the energy continuously radiated by the universe falls in the infrared, ultraviolet, radio, and X-ray ranges. For the unaided eye, this entire energy flow simply does not exist. It is invisible. Even photons that once carried visible light may cease to be so. As space expands, their wavelength grows and their energy diminishes, and the observer sees darkness, where a continuous stream of radiation physically exists. This effect is not a rare exception, but the fate of most radiation from distant objects in the universe. The greater the distance, the stronger the shift, the lower the visible brightness. In the end, even a vast number of stars cannot make the sky bright because their contribution is distributed across three dimensions at once: in space, in time, and in spectrum. It should also be noted that light does not accumulate indefinitely. Photons do not form a static background that would persist independently of motion and changes in space. They travel, interact with matter, change energy. Some are absorbed by the interstellar and intergalactic medium, converted to heat or re-emitted in other wavelength ranges. All of this further reduces the brightness of the starry sky. Thus, the limitedness of the observable universe is not a deficiency of observation, but a fundamental property of reality. The darkness between the stars arises not from a shortage of luminous objects, but from a combination of temporal horizons, spectral limitations, and the dynamics of expanding space. What seems like emptiness is in fact the boundary of available information. In this boundary is concentrated far more meaning than in the bright points that immediately catch the eye. But even within what we do observe, another law is at work, one that explains why even visible stars cannot make the sky truly bright. Imagine billions of candles placed in different directions at colossal distances. Each one is burning, but by the time the light of each reaches you, it has already spread so thin through space that its presence becomes barely distinguishable. Any source of light radiates energy evenly in all directions. In a vacuum, this radiation propagates, forming expanding spheres. The surface area of a sphere grows in proportion to the square of the radius. This means that the same amount of energy is divided over an ever larger area. Per unit of surface, less and less light arrives as you move away from the source. This law explains why the brightness of a source diminishes with distance far more quickly than intuition would suggest. Doubling the distance leads not to halving the brightness, but to a far more radical reduction. On the scale of the universe, this means that the overwhelming majority of stars, even with their colossal combined number, contribute to the general illumination of the night sky, an amount practically indistinguishable from zero. Each star illuminates only a vanishingly small fraction of the surrounding space, and light from individual sources almost nowhere overlaps enough to create any perceptible bright background. This principle becomes especially vivid if you imagine an idealized universe evenly and infinitely filled with stars. In such a model, every line of sight would inevitably end at a star's surface, and the sky would be entirely bright. It was precisely this imagined contradiction that once attracted the attention of astronomers and philosophers, giving rise to the paradox of the dark sky. However, the real universe does not match these ideal conditions. Its structure and dynamics make such a picture impossible for a whole range of reasons. The scale of human perception also plays an important role. Our sense of brightness was calibrated within planetary distances, a few light minutes at most. Under such conditions, the decrease in light intensity seems gradual and not overly dramatic. But cosmic distances exceed this everyday experience by many orders of magnitude. What at a local scale looks like a modest reduction becomes, in interstellar and intergalactic space, practically a complete disappearance of the signal. Light from distant stars not only fades, but also competes with other faint sources of natural background radiation: interplanetary dust, the glow of Earth's atmosphere, the inherent characteristics of observational instruments. Against this backdrop, the contribution of extremely distant objects becomes even less noticeable. The sky appears black not because there is no light at all, but because its intensity falls below the threshold of perception. It should also be noted that the human eye has a limited ability to accumulate light. It does not sum photons indefinitely. If the flux of radiation falls below a certain physiological threshold, an image simply does not form, no matter how many sources are producing it. Billions of the faintest signals do not necessarily add up to a perceptible brightness, if each is below that threshold. The law of diminishing brightness with distance is one of the key explanations for the darkness of the cosmos. It shows that the number of stars by itself does not determine the appearance of the sky. The decisive factor is how light is distributed in space, how quickly it fades, and what the limits of its perception are. In this logic, darkness ceases to be a paradox and becomes a natural consequence of the geometry of the universe. Beyond distance, there is one more dimension in which light disperses: time. The night sky is not an instantaneous cross-section of the present. It is a layered archive of the past, where each star speaks of what was happening millions or billions of years ago. Every ray that reaches our gaze carries information about the state of its source at a specific historical moment, sometimes in the very distant past. In everyday experience, this effect is almost imperceptible. Light from a lamp or the sun comes so quickly that the delay goes unnoticed. But on cosmic scales, the situation is different. The distances between stars and galaxies are so vast that the travel time of light is measured not in seconds or days, but in years and millions of years. The universe we observe is not an instantaneous cross-section of reality, but a complex mosaic of different epochs. When we look at a distant galaxy, we see it as it was at the moment that light was emitted, not as it is now. For the most distant objects, this means looking into the earliest periods of the universe's existence. Some of the light that could have filled the sky simply has not had time to reach Earth yet. It is in transit. And if the space between source and observer is expanding faster than radiation can travel, that light will never reach us. This circumstance introduces the concept of the observable universe. This is not the boundary of space itself, but the boundary of available information. Beyond this boundary, stars, galaxies, and entire structures may exist, but their light does not reach us in time. The darkness of the sky is partly a consequence of the fact that we see only a limited region of the cosmos, defined by the age of the universe and the speed of light. The finiteness of the speed of light also means that not all sources that ever existed contribute to the current brightness of the sky. Many stars have already ended their existence. Their light may have been bright in the past, but has either already passed by Earth or has dispersed so much that it has become imperceptible. The cosmos does not keep light as a permanent background. It transmits it, leaving only transient traces. This temporal aspect often defies intuition. It seems natural to assume that if a vast number of stars exist in the universe, their light should accumulate and gradually fill space. But light does not behave like matter. It does not settle, does not accumulate, does not form a permanent background that would persist independently of motion and changes in space. Each photon travels along its own trajectory, and if it does not encounter an observer, it makes no contribution to the visible picture. It is also important that the universe itself has a finite age. This means it had a beginning, and before that beginning, there were neither stars nor light in the familiar sense. Even if we suppose that stars began forming very early by the standards of cosmic history, some time elapsed between the birth of the universe and the appearance of the first sources of radiation. This further limits the amount of light that could, in principle, have filled space. Time and distance in the cosmos are inseparably linked. The farther the object, the deeper into the past we look. But this also means that light from extremely distant sources can be so weakened or altered that it falls outside the possibility of perception. It physically exists, but it does not become part of the visual experience. The finiteness of the speed of light introduces into the picture of the cosmos an element of incompleteness. We see not everything that exists, and not everything that ever was. The darkness of the sky in this sense is a reminder of the limits of observation. It does not signify emptiness, but reflects the fact that the universe is considerably larger and longer in time than any picture directly available to a person. Thus, the night sky is not only a spatial, but also a temporal structure. Its black background is formed by the fact that light has a path, a duration, and limits of reachability. Each visible star is an exception against the background of general darkness, a trace of the past that happened to coincide with the present moment of observation. And the space itself between these epochs is not a passive backdrop. It lives, continues to change right now, slowly and continuously. And this change directly affects every ray traveling through it. The expansion of the universe works like an invisible mechanism that constantly makes the sky darker, not by extinguishing stars, but by stretching their light into invisibility. If space were stationary, the picture would be entirely different. Light from distant stars would gradually accumulate and create a significantly brighter background. But in the real universe,